professor at the University of California, Irvine, in sociology, statistics, computer science, and engineering, at least. I may have added a few more since last time I looked. He is one of the most sort of deeply knowledgeable persons on these sorts of models and statistical aspects of networks that is currently practicing today. And so it's just really great to have him here. Almost all of you have used his tools probably this week. If you've used any of the network stuff, any of the StatNet stuff, SNA, all of these pieces on the R, are Carter's fault. And so it's one of those times when it's a good thing, not a bad thing. So we're really glad to have you here, Carter. Thanks for doing it.
Well, thanks so much, and thanks to all of you for coming out, and certainly thanks to Jim for this great invitation. So I'm going to share with you today some ideas that I hope will be helpful to you. And we're going to talk about a few things. So I'm going to start with some kind of big picture thoughts about in silico experiments. Some of this is stuff that some of you may be quite familiar. Some of you may not have thought about it much before. But we're going to talk at a high level about some of the ways that we can use computational experiments to probe social mechanisms and even things that might inform study design. And then I'm going to talk a bit about relational event models. And I think there's been some discussion of relational event models so far. I'm not sure if it's true or not based on looking at the schedule I was sent. I think there'll be some later. But we'll talk a little about that, how REMs work, and then time permitting, dive in a bit and talk some specifics about how you can use StatNet to do some of these experiments with relational event models. And in conjunction with that, I don't know if Jim has posted that or sent that around or not, but there's a tutorial here that because I love you so much, I have made just for this very group. So there is a tutorial StatNet tutorial now for these in silico experiments that you can run through at your leisure, but I'll go through highlights of that as well during our session today, and so that's something that you can also use. So what are we doing here? We're doing experiments with real life models, okay, rather than real life people, and that is an idea that is not new. Okay, every now and then this weird thing happens where people decide that, computational social science is this new, amazing development that just was invented last week by me and my friends, usually is how it's written in the papers. And that is, I hate to tell you, not true. Computational social science, depending on how you want to define it, it goes back before modern computing hardware, actually. I mean, you look at like the early some of the early experiments people were doing with little checkerboard models, Conway and his buddies, without an actual computer even to do the calculations. But certainly, from a more modern standpoint, people have been doing this since the 60s, 70s, and the early work, and then definitely the 80s and the 1990s. There's a lot of work on that. And some of us are now old heads enough, I suppose, to remember the days of doing this with agent-based models back in the 90s, or whatever. When Jim and I were mere larvae, and back in the day, I cut my teeth originally as an agent-based modeler, and all we did were computational experiments. So we posited models of social process and structure, and we changed the mechanisms in those models, and we tried to figure out what they could tell us about the world. So this is an old idea. But nevertheless, not that it was ever completely given up, but it kind of went somewhat out of fashion, let us say. It was no longer the center of work, at least in mathematical sociology and allied fields. But recently, I would argue, it's been making more of a comeback, and people are getting interested in these ideas again, or more interested in them. And so we might ask the question, why is that true? If this was like the hottest thing in the 90s when people were like listening to Prodigy and running models and like that might have nostalgia for some people. Some people are like, oh my God, Dad, don't tell me this kind of stuff. Okay, why would we do this retro thing? Well, I think there's several reasons for a renewed interest in this type of work. One of the things has to do with what's happened since then. Okay, so in the intervening time between the grand fluorescence of agent-based models in the 1990s And today, what's happened has been there's been a statistical turn in the field. And you can blame that on a generation of people that involves like, us. Okay, so that's what, we did, is we inherited all these great ideas that people before us had created about how to take, on the one hand, how to take models of social process that had very rich mechanistic detail, but were not based on reality in any way, shape, or form. I once got, more or less kicked out of a conference for suggesting to people that maybe we should actually make the models such that you could fit them to data. And I mean, the scoffing in the room, and you don't understand how science is done. Actual statement, right? And I'm like, well, I think one of us does, but anyway, I'm not sure who it is. But I mean, that's to tell you what the world was like back then, in the old days. And so what we inherited, though, these brilliant ideas about how to model things that were very deep and thoughtful. But then there were, of course, you wanted to make them grounded in reality, right? We wanted to be able to test models with data. We wanted to be able to be wrong, right? It was supposed to have this agent-based model that has virtual people living in a virtual world doing virtual things, and you think you get some insight, but then if someone is like, well, how can I test that? You're like, well, all you need some people and put them in a toroidal grid and then have them play these games, and you're okay, nobody does that in real life. How do you test that thing? Right? We wanted to have something that was statistically well-founded. The problem there is that what we had inherited a lot of brilliant ideas there too, as long as you wanted to fit linear models to things. So you could have all the statistics in the world you want as long as things were simple. And so what a lot of people in the field did over the last 20 years or so is to say, we want to take these two threads and we want to put them together. We want to have models that we can believe in mechanistically that make some sense, and we want to have real statistical meat behind it. And a whole lot of people worked on that. And have tried to put that together, and that's something that I've worked on, other people in the room worked on, other people outside this room did a whole lot of important work on that. And that has led to a real revolution that you're now inheriting today, and that you've been hearing bits and pieces of. And so now we have ergoms and SEOMs and SABs and REMs and all kinds of other things that allow us to take data about the complex world of the social ties people have and the things they do, and actually estimate from that data parameters that tell us about what mechanisms seem to be active and how they're working and so forth. And we can even simulate from those things and learn things about them. And that's a real revolution. And so now, where we are today is now we have models that we can kind of believe in a little bit, at least. You should never believe too much in a model. Model's a model. But they can capture reality in a way that was not feasible 20 years ago. And so that has opened up now the gates. And now that we have these models, now we can start to do really rich things with them. That we can go back to a lot of the ideas people had in earlier eras about how to use models, but now we can use them, we can apply them to these new generations of models that are empirically calibrated. And so that, I think, is one thing that's leading to that comeback. I think another thing is that I would argue we need models more than ever. Why? A lot of things. One, you may have discovered this, data collection is expensive, and it hadn't gotten any cheaper, and IRBs haven't gotten any easier, right? And so you want to go out, you want to collect data, you need to know what data to collect. And that becomes even more true when you want to do things like intervention studies or the like. You're going to go and intervene in real people's lives, you better make it count, okay? And the demands on us to do that in a smart way from NIH and others get only bigger. And so, the idea that, well, I'll dream up an intervention and maybe I'll do sort of a pilot, but let's just go out and try it. I mean, that's a nice idea. That gets less and less feasible. So we need to have ways of having an idea before we go out in the field for what might happen. And models are not perfect, but they can provide, some insights that can help guide that process. And there are people like Tom's in the back of the room, obviously has cared about this for a long time, right? And has been yelling at people for a long time to think about these issues. So he's one example of someone who's really, really tried to push that. And I think this is really important. And also increasingly, we have policy questions that people want to use networks for. So we need to be able to have some idea, and models can provide us some idea of what might happen if we go out in the world and we do something, whether it's collecting data or acting on people. And so that's another reason. And then another thing, and this is polemical, but Jim asked me to be here, so he's going to get opinions, right? There is a certain disease that some parts of our field are prone to, let us say, where we think about models as a fancy method for doing, t-tests, basically, So I have the idea that what I'm going to do in my life is I'm going to come up with a theory, and I'm going to express the theory in a coefficient. I'm going to collect data, I'm going to fit a model, and I'm going to do a t-test or a wall test or whatever test with my coefficient. And if it's significant, I'm going to declare victory and go home. I have learned something about the world because something was significant, p less than 0.05. Well, you can do that. But there's a limit to that as an approach to understanding complex systems, right? Life ain't a regression know-how. Okay, just because you fit something and you got a parameter that was significant, what does it really mean? What does it tell you about the world? What does it tell you about social dynamics? You learn something from that, but the something you learn is pretty meager. And I think as, early on in this development, and this I will kind of blame those of us who've been pushing things in that direction, there was so much effort to now we can test hypotheses, and okay, people wanted to do that. And they did that, and they learned some things, but after a while, you're like, we need to get some real quantitative insight. Right? If I've got two networks and I study them, in both cases I find, oh, look, there's race homophily. Okay, that's great. You've learned that. But that doesn't tell you very much. How strong is that effect? How does it interact with other things, okay, in terms of actually producing social outcomes? Right? For that, you need to go beyond just saying, there is an effect and it's here. Okay, I can measure, I can detect it. I need to know what it does. And I can, of course, I have a coefficient. I can look at the size of the coefficient. What does the size of the coefficient mean? Okay, I can say, well, all right, it changes the log odds of a tie by whatever. Yeah, but when I include all the other things in a complex system, all these things feed back on each other. And to understand that, what do we need? We need simulations to do that. So all of these things, I think, have been pushing us to try to say, let's take these models that we now know how to fit, sometimes at least, and actually try to use them to get insights. And so this is something that I think there's an enormous amount to do. And it really does represent going back to old ideas about theorizing, but using them in new ways with new tools. And there's a lot of great opportunities here. So again, I'm going to talk about some of the basic ideas of the area. There's a lot more that could be said, and then some details with REMS. And just to remind you, right, you will be able to do your do-it-yourself thing with the online tutorial as well when you discover that whatever I said is no longer in your head. All right, so let's talk about computational models. There's so many ways to do this. I certainly cannot say them all today here, but let's try to fix ideas a little bit. So I'm going to talk about one kind of broadly useful recipe for doing models of the kind we're going to talk about today, sort of informally, semi-formally, I guess, summarized. To me, this is informal, but you're like, it's got math in it. It can't be informal. Well, it's informal math. All right, I got to have some notation or they take my license away, So, all right, so here's the idea. I start with some idea of model. I'll call that M for model, very creative, okay, which we can think about as, for the time being, as some kind of black box that you give it certain inputs and it's going to produce outputs that represent a social system. What are those things? Depends on your setting, right? It might be it's going to give you a network or distribution of networks. Maybe it's going to give you interaction sequences, which is later what we're going to look at. But for the time being, we're just going to say whatever it is, it's M. And we're going to assume that the model has two kinds of inputs that we're going to think about things. One is parameters, and in our context, we're going to think about parameters as expressing the presence and strength of different kinds of social mechanisms that drive that model. There are other ways to work with models, but for today, that's how we're going to think about it. And then there are covariates that represent fixed things about, say, the agents involved in the system, the context, other features of the system itself that are going to drive the model. So the model is going to represent kind of social processes that take mechanisms and the strength of those mechanisms and the substrate of who's doing things and what the context is. It puts them together to produce some kind of output. So we start with, we have to posit some kind of model or we got nothing to do. So we're going to posit that. And then we assume we also are going to observe with some observations. So we start with some observations. So we've got some data. And then the first step in our recipe is we need to calibrate our model, right? And that leads us to some, we'll deign to call them theta obs, although that's really our estimates, and x obs. How we do this is, well, you've seen talks about that. That's a whole other set. I'm going to assume you've done it for our recipe, but that's the first step, right? And so obviously this step takes a lot of time. But you've got some kind of model. That's the first stage. Now, once you have the model, what do you do with it? Well, the next step in our recipe is we need to pick some kind of quantity that we care about. How do you pick that? That's on you, not on me, right? You need to know what you want to know, right? What do you want to know about the system? Maybe you're interested in smoking in high schools and the prevalence of smoking X packs a day is your outcome. Maybe it's something else. Maybe it's social isolation. You're interested in what fraction of students have no friends. Of course, then you have to be careful. Do you mean friends in the school or friends in general? But that's on you. You have to decide that. But we're going to let F be whatever that statistic is of substantive interest, something that you can measure from the output of the simulation. So that's the next thing you have to do. So you have to decide what your model is, and you calibrate it. You have to decide what you care about. And then the next step, which nobody likes, but an important one, is checking model adequacy. So the next step is going to be you're going to simulate from your model out that social outcome, and you're going to compare what you see from your model to what you see in the data. And again, there's lots of ways to verify model adequacy, lots of ways to assess it. Here I'm just going to include it as a list of in our recipe. But the basic idea is you want to see, is it plausible, at least the model reproduces what you saw at empirically at a sufficient level to be useful to you. Okay, having assessed that and validated that your model actually does reproduce the world reasonably well enough that you can trust it for your purposes, you now are ready to actually do something. And then what is the thing you do? You first identify a set of conditions that represent alternative choices of theta and or x. So other kinds of social mechanisms that could be active, or other kinds of situations that the network or the system could be in that you want to examine. So we can think of those as pairs of thetas and x's. Then again, how do you pick that? That's on you, although we'll talk a bit about how. But these are going to represent our different theoretically interesting circumstances that we would like to simulate. Then for each condition, we draw a sample from our model of the potential outcomes, and then we use our favorite methods to analyze that to figure out what difference are theta and x making to f with respect to our model. Okay, that's the basic recipe or meta recipe. There are many, many variations on that theme, okay? So there's a lot of things you can fit in here, but it's kind of handy to have, if you've not thought about it before, a recipe in your head to think about how to structure the activity. And so if you do this a lot, you're like, well, yeah, this is obvious, but if you've never thought about it before, it's kind of handy to have that in your head. So then the question is, well, what kinds of, there's at each part of this, there are lots of different choices and things. We talk a lot about up here doing that. But I want to talk about here, this part a little bit, because you might imagine, well, we face this mind-bogglingly wide range of choices that we could have. We could pick all kinds of things to change. How do we decide that? And of course, that too is on you, right? You have to know what you want to get out of the model and what you want to probe. But it's useful to have a few common examples to work from if you're not immediately like, oh, I already know what I want to know. And so here's a set of things that I think are often really common designs for Silico experiments, which are handy. And I'm going to talk about them using terminology that I'm going to, completely, with no shame, steal from the biomedical world. Okay, and why am I going to steal this from the biomedical world? There are at least two reasons. Okay, I'll tell you the good reason and then the bad reason. Okay, the good reason is because people in that community have, for a very long time, they're mostly experimentalists dealing with like actual experiments, in vivo experiments, vitro experiments. And they have, like us, they have to probe complex systems, right? You have some kind of frog, and you're interested in how the frog sees motion, and you'd like to know that. And the problem is frogs are really complicated, and how are you going to figure out what it does? No one can give you the giant map of frog to tell you exactly how it does it. You have to figure that out. And so they've had to think about how to do clever experiments, say complex systems, and probe what they do. Our models now are sufficiently complex that we don't fully understand them ourselves either. So it's useful to use some of the ideas they have to inform what we do. Another thing that's nice about that is that many of you, this is a health meeting, right? Who funds you? NIH, that's the answer. In case you didn't know, that's the answer. You better learn that. Okay, the camera's on, here I am. But that's life, I have no shame. Who runs the panels at NIH? Okay, I'm not gonna tell you, but you can fill in the gap. Who's making your funding decisions? Okay, who runs the thing? It's the biomedical people for the most part. So that has a social consequence. right? If you can take the things that you do and the insights you have, and you can communicate them in a language that the people who have to make things like funding decisions understand, you're going to be much more effective at getting those ideas across and getting them to support you than if you try to explain it to them using like Durkheimian whatever. I mean, nobody cares about Durkheim, including sociologists, right? But like they have to pretend to. But like they don't even have to pretend that in that context. They're going to be, what are you even talking about? Okay, so it's helpful to be able to think about what you do when it is analogous in a way that allows you to then translate that. And I think you're going to have more success. So let's roll with it. So here are some examples of kinds of experiments where I'm going to use some language that we've again stolen from the field, but I think it's really nice language. And that's the idea of knock out, knock in, knock up, knock down. Okay, and so this is, the idea again comes from that I've got my frog that I'm trying to study. And the question is like, let's say I have something in that frog that I think might be involved in its visual system, say something that codes for some opsin, for instance. I want to know, well, what is it doing? That's a very hard problem to directly probe. One way I could try to do it is I could take the gene that codes for that opsin, and I could turn it off. I could knock it out. I could use RNA interference, or I could try to CRISPR it out, or whatever. And so the idea is I can reach into that frog and turn off this piece of the frog. And then I can look at what happens to the frog, the poor frog. If you like frogs, don't go into biology, because you got to do things like this, okay? But so you knock it out and you see what happens, right? So for instance, if you now discover now the frog is blind, okay, that tells you something about what this thing is doing to the visual system. Maybe the frog is not blind, but it now can perceive lateral motion but not vertical motion, okay? It gives you a clue about what's going on. And so that's called a knockout experiment. We take a mechanism, in our context, of course, it won't be a frog, it'll be from our calibrated model, and we're gonna turn it off, we're gonna knock it out. And we're gonna ask what happens. No, we don't change everything else, we don't refit the model. Because the whole point, we don't remake the frog. The whole point is that we're going to take that frog or that social system, we're going to cut this thing out of it, and we want to see what it does. And that gives us a clue about what function the mechanism had in the original setting. We'll show examples of this presently. So this is a really powerful idea, and it's very easy to do, right? Turn something off. Another one, if I can knock things out, I can knock things in. I can put things in the model that weren't there before. I could take a mechanism that wasn't present and now add it to the system. My frog, I could take a gene or say a different opsin that some other organism has, and I could stick that in and make the frog express it and see, does that change how the frog behaves? Like in a social context, we'll see an example later, we could take a social mechanism that we don't see in our observed system. In fact, to foreshadow, we can have a system where, for instance, we have children in a classroom, and we observe that in that particular classroom, we don't see differences by gender in how they interact, but we could certainly imagine cases, other classrooms where that might happen, and we could say, well, what happens if we take everything and now we add a particular kind of gender effect on behavior? What does it do to the classroom dynamics, right? That's a knock-in. So that's an idea. Of course, if we can knock things in and out, we can knock them up and down, which means that we amplify or attenuate a mechanism from its calibrated level. So if we observe a particular propensity of people in a particular social system to act in a particular way, we can say, what if we make it stronger? What does it do? What if we make it weaker? Right? So we can tune it up or down. In the real world, I can't reach into the world and say, take social influence and like, let's just turn it up or turn it down. People try, but you can't really do that. But I can do that in the computer, and I can see what happens. So that's another thing we can do. And then, of course, we can change other things as well. So we can change our covariates or our context, right? We could, for instance, modify the individuals in our setting and see what does that do to the social dynamics by changing the covariates. Change the context that we're in by changing those things from the calibrated scenario and see what effect that has. And then in dynamic models, you can also do sequence interruptions. So let's say I have a particular social process, people come into a room and they talk to each other and then someone goes out and whatever else happens. I might say, well, what happens if I let that social sequence transpire and then something happens in the middle that I alter the system, right? We can carry out those kinds of experiments as well in Silico and learn things. So these are just examples. There's many other things you can do, but this at least gives you some flavor for some of the kinds of things that we can do. And from these simple recipes, we can learn quite a lot. So let me give you some examples. I'm going to start by giving you a couple of examples, and these all come from a series of papers that I did with Cynthia Lacon and John Hipp and Cheng Wang. There's lots of other stuff that's sort of similar other folks have done. David Schaefer's in the back room. He's done a bunch of stuff on this. Jim's done related stuff. Tom's done related stuff. So there's lots of people in the room who know a lot. But I'm going to give you my examples because I'm the one giving the talk, so and I haven't. But all right, they may not be better examples, but here we have it. This is one. It was a relatively early than the stuff from our work on it. Work on this. This is from a paper again with that crew. It was in AJPH in 2015, and so this paper. We had a model that is very typical of models lots of other people have used for looking at smoking behavior and friendship in adolescence. So we were using the stochastic actor-oriented or stochastic actor behavior, whatever you want to call them, models. And this is using the ad health data set. So lots and lots of people have done work of that kind. And so what these things are picking up is they're looking at the formation dynamically and dissolution of friendships, but also substance use changing. And these things are affected by individual attributes and by social context, and also by social influence effects. And there's selection effects as well. So whether you're a smoker, might affect whether people will be friends with you. Of course, other your friends smoking could also affect you. And the idea is to try to partial out all of those effects. And there's a lot of work doing that. What we did, though, in this paper was to say, rather than just like, let's look at the coefficients, because if you fit the model, you look at the coefficients, you find reliably over and over again that, yes, indeed, people's smoking behavior influences their peers, and there's some effect on selection. People tend to select alters also that have somewhat similar characteristics in terms of smoking. Okay, and you see that over and over again pretty reliably. Now, then the question, though, is, okay, what does that, though, mean for actual smoking prevalence in schools, right? There's a certain narrative, right, that tends to be said about this that I'm sure you've all encountered, and this either in the literature or maybe in your everyday life, right? And the narrative, to caricature it, is a little like this. It's that, there are these good, wholesome kids, good kids, clean kids. They don't do things like smoke. It's bad, okay? But then those good, wholesome, non-smoking kids come in contact with bad kids who have like long hair and stuff. You can't trust those people. And they're like smoking and drinking and doing all kinds of stuff. And then when those good kids come in contact with the bad kids seduce them to evil. Okay, people they don't write it that way. Well, okay, sometimes they do. But but that's the hidden tacit model behind an awful lot of public health. It's ultimately the 19th century innocent naif that is seduced to darkness, right? And except that we say it in very clinical language and publish it. But is that really how it works? Well, how do we know? Well, one thing we could do is we could do an experiment. So we could take our model. We've estimated the propensity to smoke. We've estimated social. We've estimated how it's affected by your parents and all this other stuff. And we could say, let's go into that system. Let's reach into the system. And what if we turn off social influence? Or we turn off peer selection? Or we turn it up? What if we make it really strong? Okay, we could do that. We can modify the system. And if we do that, what should happen? Well, if it's all about being seduced into darkness, the darkness of puffing on that best stick, okay, then what should we see? When we turn up social influence, man, people will be smoking crazy. If I turn off social influence, then, well, that seduction can't work anymore. And now virtue will be left unsullied, right? Is that what we find? Let's see. What do we find? Well, we plotted some stuff. Okay, so what I have here, two different schools, the two largest schools, and here we have the relative value relative to the measured value of selection here on the left-hand side and influence on the right-hand side. One means this is what the measured value was. We move it towards 0, we knock it out over here. Otherwise, we're knocking it down, and then we can knock it up. We can make it larger, 5 times as big as it really was. And so then we have the prevalence of students that would be smoking in this simulation. And we validated that it does a good job of reproducing the data at the actual case. It's hard to read these lines, I regret to say, but if you focus on the top line is the never smokers, and they're probably the most useful case to look at here. So what happens? Well, if we vary selection, tendency of people to choose friends who have the same smoking as themselves, we find it doesn't do very much. In the first school, it does nothing really in practice. There's an effect, but it doesn't do much. And there's a little bit of an effect in our second school, but what is the effect? Well, if you turn off this propensity to hang out with people like yourself, what do we see? Well, we see never smokers go down. So this does increase light smoking a little bit. So that actually means peer selection is suppressing smoking. If you knock it out, you get a little more smoking. So that's kind of interesting. What's it doing? It's isolating smokers amongst themselves. And that isolation, right, is actually preventing smoking from spreading. Well, that's interesting. What about influence? That's not a very big effect. Maybe now in retrospect, we're not interested in selection anymore. What about influence, now that it didn't do what we wanted? Well, let's look at influence, and man, isn't that dramatic. So, here's your prevalence. What happens when you take influence down? When you take influence down, the never smokers drop. And when you increase influence, they go up. So what's happening here is that we see that social influence is suppressing smoking. It's the opposite of the seduction story. Okay? At least in this, to the extent the model reflects reality, then this says, well, actually, there are a bunch of people who would be smoking, but they don't because they're influenced not to. And if you turned off influence, they'd be lighting up. No one would stop it. And if you made influence stronger, in fact, fewer people would be smoking. And moreover, if we look at what's really increasing, these are the heaviest smokers. There's really heavy smoking that's actually being suppressed more than anything else. Okay, it's the opposite story from the seduction story. Right? And that makes some sense if you think about it. What does social influence do, fundamentally? Social influence suppresses deviance. That's what social influence does at a meta level. Always what it does, right? You, on average, by regression to the mean, are tied to people who are more normal than yourself, especially if you're weird like me, but even if you're not, this on average is true. Okay, so if you're really influenced, you're going to be more influenced to be more like the population. If the population mostly doesn't smoke, which is mostly true in these cases, on average, it's pulling people away from it. So it does the opposite of the thing that one might naively think. Very easy to see that when you do the experiment, right? You can't read that out of a coefficient. So this is a very trivial thing to do, but it gives you some insights that are pretty powerful. So that's an example where we can use knockout, knock in, or knock up and down to get stuff. What if we have multiple cases? Another kind of thing that's useful is if we have multiple behaviors at once. So here's another example we did. This was, again, same crew, a little later, looking at a whole bunch of, now we are up to a bunch of substances. We got smoking, drinking, marijuana. It's a whole party going on. And then the concern here is, well, there's a lot of potential effects, right? So you can have all kinds of complicated thing where maybe drinking is influencing marijuana use, and maybe that's influencing smoking. All of these things could be affecting each other. And when you have a complex system with all these feedbacks, how do you tell what the net effect is of, for instance, influence by smoking or drinking? And so one simple thing to do to probe it is to say, well, what if we take all the different sources of influence, and we try knocking them out one by one, and we see what does it do to prevalence? And so this is smoking, drinking, marijuana. The top line is that non-users, it's easier to look at. And so these all represent just different knockouts, where we turn off different mechanisms and we see what does it do. And so when you see a line dip, that's something that says that knocking that out increased usage. And one of the things that we see that's kind of interesting is that if you knock out the influence on each of the forms separately, it does tend to increase the substance use. So in all of these cases, on average, influence is suppressing use. But if you look at the cross, one thing that's interesting is you see this thing go up. So this is actually, there's less drinking. One of these interesting is that if you knock out the effect between marijuana use and drinking and smoking, it actually results in less drinking. So one of the few we don't see anything really affecting the marijuana use, but the marijuana use is affecting other things. Other things are affecting marijuana use, but the marijuana use is affecting drinking indirectly by this whole complicated thing of people who are using that together also are influence each other to do other kinds of things. And it's creating a whole milieu, and in that milieu, people are drinking a fair amount. And so if you turn some of that off, it seems to reduce drinking somewhat. So it's not very obvious, but the kinds of things you can discover by probing models, by turning things off. So those are just some simple examples. Another use, as I mentioned, is you could potentially use models to help give you insights about targeting for interventions, or even to do data collection. To say, if I can only do a treatment to certain units in the population, who do I pick? And there's lots of ideas about how to do that. Models can help you test alternatives. So here's a really simple case. This is another paper, again, same group. It's a little more recent. It was in Prevention Science. And what we did was we used the same kinds of models we were talking about before, again, looking at, in this case, at drinking, and just said, okay, let's imagine you're going to go in, you're going to do an intervention where you're going to get someone to stop drinking. And let's say that assume for the moment your intervention will work on the targeted individuals. That's not given, but let's say it did. What would the total effect be if you pick different groups of people? And so here it's like, well, let's take 40 of the heavy drinking students in this particular school, which is about 20% of them, and act on them, and then see what the consequence is followed up for how many people in the total school are drinking. And we can do that by picking different people to operate on. So we could say just take them at random. We could sample them by their out degree, friendship out degree. We could do their in degree. We could use all kinds of network measures. And of course, Tom's done a whole bunch of work on this kind of problem. Other people have worked on it. And what do we see when we do that with simulation? Well, the good news is that all of these interventions give you a much better return than just nothing at all. So that is actually useful in and of itself, right? We can use the simulation model to suggest that it ought to work. That doesn't mean it will, but that at least if you're planning a study, right, that's helpful to know before you go into the field that at least there's reason to think it could work. If we had done this and in fact there's like nothing, that would suggest that this probably won't work no matter what, in which case you should probably rethink. But then we can also see, okay, which of these different methods seems to have the best results? In this particular case, what we saw is that selecting people by in degree and eigenvector produces noticeably better results than the other methods. And we have a bunch of different targeting methods you can use. And so does that mean it's necessarily right? No, you have to go out and test that in the world. But this gives you an idea of where you might go. And if you're trying to justify a study design to a panel, right, at least having tested it in Silico gives you some justification for going out and now testing it in the real world. We should never, we always have to remember models are models, right? They're not a substitute for collecting data. I was at a conference earlier this year, and it was not a social science conference, so it's not, this is not a blame our own crew. And so just to show you that this happens in other fields, these were mostly structural biologists. But where there are people who are like, well, we really need to collect data on proteins. Why don't we just use, AlphaFold? We'll just use computational things to just predict everything, and now we don't have to measure it anymore. And it's sort of like you have left the path of wisdom. Okay, so we don't want to fool ourselves. But the models are a lot better than nothing. They're a lot better than guessing, and they may be a lot better than just, having done one small-scale pilot, because we can probe them, we can figure out what's going on. So as a tool to get insight, I think they're very powerful. Okay, so having hopefully convinced you that it's a useful thing to do, how do we do it? And of course, there's lots of ways we can do it. And I've been talking here about SAB models, SAOMs, but what I'm going to focus on the rest of the time is going to be a different class, which are relational event models. And all these ideas, the high-level ideas, you can use them with any model whatsoever. There's nothing special, but I want to drill in on a specific case. Why REMs? Well, I think they're nice for this. They're a dynamic framework. They're well suited to these kinds of computational experiments because we can identify specific mechanisms and turn them on or off. We have StatNet tools to work with them, which makes it convenient to talk about them. I think there are a lot of things that you can do with REMs in a health-relevant setting, especially if we get more data, especially micro-interaction data. There's a lot that can be done with this. So what I want to do is I'm going to talk a little bit about REMs as an overview, and then I'll show you some of these how-to examples. And again, there's the full tutorial that you download and work through as well that goes into depth about how to do all the different kinds of experiments that we've talked about using REMs. Now, before I get into this, I know there's been some discussion on relational event models. I know there's some more on the docket. But let me gauge. I don't want to bore people if you're like, oh, we're all REM experts. So like, how many people are REM experts, would you say at this point? How many are like REM? Okay, we got somebody who's willing to volunteer. That's good. It's going to be bold. Unfortunately, it's one of the instructors. So that's not so helpful. How about like, people who feel fairly familiar? Okay, there's some of that. How about people who are like, I have no idea what this thing is? All right, we got some people who are, okay, good. Well, that's convenient because I got slides for you folks, and the rest are going to be bored. But we would skip it if everybody knew. All right, so let's go back to the beginning. So what are relational events all about? And to understand what relational events are about, we have to understand what networks are about, which we thought we knew. But let's look at it from a new standpoint. Right, in the conventional network paradigm, something that you have probably never bothered to think about is that you study things that have temporally extensive relationships. You have, say, a friendship. The friendship has a beginning. It may have an end. But in between, there is a non-zero period of time, or else it's not much of a friendship, right? And you may not have thought about that, but that is essential to everything we do with networks. Networks are all about coterminous relationships, right? It's all about the fact that I can have a relationship with you, and they're present at the same time. So for instance, you can influence me and I can influence you through that relationship, okay? You can give me a disease, I can give you the disease through the relationship, and so forth, right? And that's an essential feature of what we do with networks. And it's wonderful and powerful and fun, and we spend our lives doing it because it's awesome. But sometimes we're interested not in that, but in social action that lies beneath the relationships, back and forth interactions, okay? And those are a bit different. And to appreciate that, let me take you back to, whether you like it or not, to an example that was really the motivating example for me that led me into this, which was a case study we were doing. And it's not, well, in a way, it's health relevant, but not in a normal way. This is some work we did on the World Trade Center disaster. And so what we have here on the left is a network of radio communications among agents at Newark Airport, trying to close down the airport on the morning of September 11th, 2001, when of course, all air traffic in the US was shut down. And so these are individual agents. They have fixed frequency radios. They can talk to each other and no one else. And they are calling each other as they try to figure out how to get this thing shut down. And we can, of course, analyze this by taking does someone call someone else during the time period of observation and make a network out of that? We can even weight the edges by how many calls they have. And we can learn a lot by studying networks like that, and we have. But there are limits to this, because what's really going on is not that, okay? It's not that people are sitting embedded in this network where they're in constant communication with certain alters. This is what's happening. Okay, so the real data looks like this. You've got people calling each other back and forth, as they try to coordinate, as they try to figure out what's going on, what's happened, what do they need to do, and so forth. And so if we really want to understand the mechanisms that give rise to this, we need to deal with this. But this is not a network, right? These are not temporally extensive ties. These are micro interactions. And we need a way to think about that. And that led to the creation of what we call a relational event paradigm. So what's a relational event? It's a discrete event in which one or more entities emit a behavior directed at one or more entities in their environment, possibly themselves, if you read your Goffman. And so we can think about it as time goes on, and in time, the actors involve exchange interactions. And so we can represent just like you think about representing an edge in terms of a pair of you have the sender, the receiver of the edge. We can think about relational events that way, sort of. But we can think about them like this. So they have a sender who emits the event. In some cases, that sender could be collective, it could be more than one person, but we have a person or group that emits the event. You've got a receiver, person or group receives the event, which might include the senders themselves if it's a self-interaction. In some networks, you have different kinds of interaction that might matter. And then, of course, though, it has a timestamp. And this is the key thing that makes REMs different, is that we can think about these relational events as being discrete entities at a particular moment in time. Now, that's not exactly true. Everything takes some time. But relative to the overall social dynamics, we can think about relational events as things that we can approximate as being instantaneous. And that means that they're well ordered. And that changes the whole game, because we're no longer thinking about, again, networks that are things that are present at all times. We're thinking about sequences of interactions. And this makes a difference. Again, going back to the motivating case, we did this early work. We had not just that one network, we had a bunch of networks involving responders to the WTC disaster. This is an example of, again, a time-flattened network from, these were operators in the WTC complex themselves. They're trying to get to safety. They're trying to figure out who's alive and who's dead. They're trying to figure out what do we do as they self-organize in response to this event. We can learn a lot by an aggregate network analysis. So I'm certainly not criticizing that. I spend most of my life doing it, right? And we learn things like these networks are mostly held together by these coordinators, and a lot of the coordinators are emergent. That is, they're not people whose job it is to coordinate people like dispatchers, managers. They're people who just seem to have just risen into the situation. Raises the question, how does that happen, right? That's a dynamic question. We can't get that from this. But we can see there's a high prevalence. We can compare specialist networks and non-specialist networks, and we find actually they're very similar. And we can even look at the role structure that we see, which has this sort of four role structure. But when we wanted to get at the mechanisms behind that, where did that come from, right? We had to get at these micro interactions, and that was where we needed this new approach. So I guess to highlight, this early work was done largely by my students Maruna Petriska-Prahova and Remy Cross did a lot of the hard work in coding data on this as we were trying to figure it out. And so that drove us to think about, okay, how do we think about modeling events like that? So we've got sequences of events in time. And we draw here a lot of inspiration from other threads that have thought about events in time, like event history analysis. So we can think about this as we've got multiple actions that we're looking at, and they form an event history. So at capital A sub t represents all the events that have happened up to some time t. So we might have something like, say, this classroom data from Dan McFarland. You have instructor, you have people in the class. They're talking to each other. In some cases, you see the instructor addressing the whole class. In other cases, students interact with each other, and so forth. But at any given time, right, you have nothing happening, or you have a single event. At any given moment, there's a set of possible events that can occur, which could be a function of the event history. And that is just going to be some subset of the Cartesian product set of possible senders, receivers, and things they might do. So that's going to form the support for the next action. And our goal then is to model the actual event history. And we do this by treating the actions as events in a statistical sense in continuous time, whose hazards depend upon the past history and covariance. So you're going to have occur at any given time. There's a history up till now. There are covariates. Those are going to determine the context for interaction. They're going to create propensities of different actions to occur. Then, sooner or later, something happens. Those events may in turn change the propensities as people react to what has occurred, and that sets the stage for the next action, and so forth. And it turns out that if you posit that kind of model, you can write it down, and it looks like this. So we can use very straightforward ideas from event history analysis, hazard modeling, survival analysis. Depending on the field you're in, it's all the same thing, but people have different languages for it. And what it does at the end of the day is it allows us to take the propensities for actions or events to occur and write them down involving a hazard function, which we parameterize like so. So you remember the ergom thing. This looks a little bit like that. Not exactly the same, but similar. So this is the hazard of a particular event. Think of the rate at which it would happen if nobody intervened. And we can write the log rate as a linear combination of statistics. We often just separate out the pacing function. That's just an overall average speed. But the main action is in these U functions. And the U functions are like the statistics in ergom. They are arbitrary functions of the sender, the receiver, the type of event when relevant, the history up till now, and covariates. And they say basically how likely the event, or how rapidly that event would happen. And these parameters theta govern those things. So these are the mechanisms that drive action. These are the weights on those mechanisms. If we assume that and some other simple, typical regularizing conditions, we can write down the likelihood. It looks like that. It's beautiful. Love it. Memorize it. Anyway, it's there. And the advantage of having that is then we can do inference in the usual way. And so having then an observation of an event history and having chosen our model terms that express the mechanisms that drive interaction, we can now estimate coefficients. And since we've got a likelihood, we can do all of our favorite likelihood things. You can get MLEs if that's your preference. If you're a good person, i.e. a Bayesian, you can do this in a Bayesian way. It's all good. We can do all these things. If you're want to be a good person, but you don't want to admit it, you can do penalized. You can actually do the same thing, but call it a penalized MLE, and then you don't have to feel like you're a Bayesian, but you can be one. Doesn't matter. We can do all of these things. And in general, the computation is not so bad. Compared to ergoms, it's a lot easier than ergoms. So that's another thing that's kind of nice about these things, that although they're not super cheap, they're a lot cheaper to fit. And so that's a bit about what the models are. Now, of course, the question then is how do we use these things to do the experiments? And so in the balance of time, I want to go to this little tutorial. And there's not going to be time to go through all of it, but that's just as well, because that would get quite boring. especially because you can download and look at that. But what I want to do is highlight a few specific examples and give you a flavor for it, and we can then take it from there. So let me drag it over. So here is, again, the tutorial, and hopefully that's been made available to you. So this is set up in the same way as all of our tutorials. If you're not familiar with them, we have a whole bunch of these things that we put together in the project that we try to use a sort of similar style, and all of them are made so you can kind of copy pasta examples and run them. And so you can use this as well. And just recommend representing for the team. There are a whole bunch of folks involved in StatNet, involved in different aspects of development. So lots of people contribute to all this stuff. And so this will walk you through how to install it. We're using a package here called Relevant, which is the relational event package. That's why it's called Relevant and not Relevant. Once you start typing this, you'll become unable to spell relevant correctly. This is a side effect when it takes, this is a side effect of the thing. One thing, I want to point out, so if you do download this, there's a little DAR data file you're going to need that has the data we use. Also, if you're on a machine that has parallel processing, I encourage you to set this parameter in there to something greater than 1, because some of the examples take a while to run, and this will speed up the process considerably. Okay, so the front part is just going to talk through stuff we've already talked about, so I'm not going to talk about here, but you can read through at your leisure. It says the usual thing. And then we have a bit about the models we use. So in the tutorial, we use 2 kinds of models, or 2 different models, both of which were conveniently created in an earlier REM tutorial that you can also download and use. And so one is from an example from that World Trade Center data, and the other one is an example from Dan McFarland's data. And both of these are models that sort of work pretty well, and so they're good to start with for our experiments. Today, for one of time, I don't want to go too much into that part of things, but I'll just point out basics. So what does our data look like when we do REM stuff? There are these event lists or edge lists that look like so. So you have an event number or time. In this case, these events are only known ordinally, so we just have the order in which they occur, but in many cases we have exact timing information, and that would go here. And then you have a source and a recipient. So it's the number of who sent the event and then who received it. These are called dyadic relational events because they're between pairs of actors. So the police calls looks like that. If you flatten the network, this particular thing looks like this. So these are police units that were in the World Trade Center, or it's a police unit that was in the World Trade Center disaster at the time. The green notes here are individuals who occupy what we call an institutionalized coordinative role, or ICR. That means it's someone who is like an officer, a dispatcher, a manager, someone whose job is to coordinate other people. Now, that's their job, but of course, when the plane hits the building, all sorts of things start to happen. Now, that doesn't mean that they necessarily will wind up being the ones who do the coordinating. Now, if you look at the network, the biggest coordinator in this network is an ICR, so that kind of plays in with the theory, but then this isolate is an ICR, and they're not coordinating anything. So it's not so simple, right? As we might imagine, other things are going on, and indeed that turns out to be true. So the way we fit models here is we use a command called rem.dyad that says relational event model, dyadic form, and we pass it the event list, we tell how many nodes there are, and then we have a thing called effects. This is what effects are put in the model. And if you get the help on this, there's a giant list of different things it knows how to do. In this particular case, we have effects that wound up in the final model that include a tendency toward interaction if you're an ICR. So the idea that ICRs are more likely to be interacted with and interact with others. Turn-taking behavior, this builds something that David Gibson came up with many years ago called participation shifts or P-shifts. These are really powerful terms, actually. And the first one has to do with turn-taking. So I call you, the next thing happens is you call me back. And remember, these are radio people. So on radio SOP, the standard operating procedure, has a lot of rules about how you communicate with people, and turn-taking is really critical, because otherwise no one understands anything. If you were a kid and you played with a walkie-talkie and no one could figure out what's going on, it's probably because you didn't have good radio SOP. So, if you read the transcripts, it's like, 41, calling 49, over, and then 49, 49, this is here, go. Okay, well, such and such, and then there's this call response thing. And you need that because that coordinates activity and lets people know that, I heard you, I understand what's going on. And so, but then there are other things that can happen as well. So for instance, baton passing. I call you, you now pass on to someone else. You call somebody else. Sequential address. There are also other effects like recency effects. So if I'm picking a target in a disrupted environment, who am I going to call? I'm likely to call other people I've interacted with recently. But from an egocentric standpoint, it doesn't have to do with who other people have interacted with. Who have I interacted with? So we have terms for things like that. And then a preferential attachment sort of term, if I don't know who to call, who might I call? Maybe other people who've been on the radio a lot might be natural targets, right? And the more I'm on the radio, more people hear my name, they think, oh, Carter's still alive, I better call him. Okay, he'll know what's going on. And then that means that they call me, now that puts me on the radio more, which means that now more people hear me and they're likely to call me, right? And so this can become a mechanism of emergent coordination formation. And so we have those things in there as well. If we fit the model, we get something that looks like so. And again, the other tutorial goes to that in much depth, but this just gives you a flavor of what the models look like. So we have our different mechanisms, and we have coefficients that say how strong those mechanisms are. And of course, we have our usual statistical tools. But our focus here, right, is not on the model per se, but on what we can do with the model. So I'm going to sort of jump forward a bit and talk about that. I will point out we do have some adequacy checks here and things. Model, by the way, that model works sort of surprisingly well at first blush. If we ask the model, even do something as difficult as say who will call whom next on the radio, which is a pretty difficult task to get exactly right, it gets exactly right about 68% of the time, which you would think would be impossible. You have a disaster, how on earth can you do that? And of course, the dark secret is because conversations are very structured. And so you can often figure out once conversations dynamics go, who is likely to have the next action and whom. So like all things, there's a reason why you can predict it. But anyway, but the model does do a good job of that. McFarland's classroom data, these are classroom interactions. We've got a couple of teachers here and students, and we can model that as well. And I'm going to skip ahead, but you can look at that. It works pretty well, not quite as well, which tells you that classrooms are much more difficult to study than the World Trade Center disaster. And you know, two kinds of disasters, the classroom is the harder disaster, which may make some sense to you. So how can we then do some of these experiments with these kinds of things? So let's start with a knockout experiment, right? That's the simplest thing. I want to take some kind of mechanism and turn it off. How do I do that? Well, the first thing we need to be able to do is to simulate. And in the relevant package, we have a way of doing that. We have a method called simulate, which if you're familiar with the ergom simulate command, it's very similar. We pass it an object, but it's a rem.dyad object. And we tell it to simulate it, and it will simulate new social outcomes, new realization of event sequences from that model. Okay, so in this case, new radio communications, if we use the model we just talked about. And by default, it will just reproduce the model that we have. It will generate a new realization from it. But we can change things about it. We can change how many events we simulate. We can change the coefficients we use. We can change the covariates and so forth. And so the tutorial will walk you through doing that. But what I want to do is skip to then how we can use that to do a knockout study. So focusing on that WTC case, right? One of the things we've observed from our cross-sectional work is that on the one hand, the network is held together by coordinators, but then who those coordinators are is very hard to predict. And sometimes it's people with ICR roles, but often it isn't. ICRs are overrepresented. They're more likely to become coordinators than random people, but most of the coordinators in the whole data set are not actually people with ICRs. They're regular folks who wind up in those roles. How does that happen? Okay, well, there must be different endogenous mechanisms producing those hubs. What might they be? Well, there's a lot of things you can imagine, but one that you might at first not think much about, but that in fact turns out to be very important is turn-taking. So we're going back to this turn-taking idea. Now, why would turn-taking have to do with emergent coordination? Well, if you think about it, right, when you have turn-taking, that creates an inertial effect, right? If I start a conversation with you, we're exchanging events back and forth, and that puts me on the radio more. And the more I'm there, the more opportunities there are for someone else to call me, right, and now get me in another conversation. And more people to hear me and know that I'm still there, and thus someone they might call. And so conversational dynamics like turn-taking tend to create inertia that locks the same people in the conversation, and that may give them more of an opportunity to wind up becoming coordinators. And if a random person just happens to be the person all the action centers on, they might wind up becoming the coordinator instead of the person who otherwise would do it. Maybe that's true, maybe it's not. How do we know? Well, one thing we can do is we can knock it out and see what that does to coordination. In particular, we can see if you knock that out, does that become more strongly associated with being an ICR than if it's there? And so how do we test that? Well, what we can do is we can just build a simulation where we simulate draws from the network, but where we turn off that effect. And how do we do it? What we do is we take the coefficient vector from the original fitted model, that's what this is, and then all we do is we take the p-shift effect that has turn taking in it, and we just turn it to 0. We just turn it off. And then we use the simulate command, and we simulate new draws from the network with that knocked out. Now, we also, of course, need to simulate draws from the control. And what's our control here? Our control is the network that doesn't have it knocked out. So we can compare a world that works the way the data suggests and a world that works like this knockout case, and we can see what happens. We also have another model that we throw in as a point of comparison. We could have a different model where instead of knocking things out, we only put one thing in, and that is we just have a tendency for ICRs to have differential activity. And so that's another kind of almost positive control, where we say we're going to have a model where the only thing that matters in the world is, are you an ICR? And that has obviously, that should give us the maximum association between being a coordinator and being an ICR. And this point creates a point of comparison. So what this thing does, it just does a loop. It does this in a parallel way. So MCL applies a parallel loop function, and it will produce that data. And the outcome measure we're using is the correlation between betweenness and having an ICR role. So are you brokering other people or not? And if we look at the results, they look like this. So these are just box plots of that correlation. The left-hand side, we have the world where ICR only is what's going on. We fit a model with just that. So that's kind of our positive control. We have a model that's the full model here, and then we have the model that's the knockout model. Then the red line actually represents data. Remember, we need to make sure that this is compatible with the data. So does the data cover, or is the data covered by the real model? It is, so we consider it adequate. We can see it's not dead on. The model wasn't trained to do this particular task, so it's not perfect. But it's certainly, the data is certainly something, a plausible thing that could have come from the model, right? So at least it's within the range of what we produce. So, okay, that's reasonable enough, but then what happens when we take it out? We see that, in fact, the correlation goes up. So what that's saying is that, indeed, turn taking is knocking down the effect of the ICR status on who becomes the coordinator. So, indeed, it's compatible with the idea that turn taking is actually helping to produce emergent coordination. And so that is then interfering with other mechanisms. Now, is that good or bad? That's a different question. We're not passing judgment on it, but we are saying that's what seems to happen. Now, that's just a knockout. We just took the effect out. But we could also, of course, try knocking it up or down. We could change the strength of that effect. And so how do we do that? We do the same kind of experiment, except now we're going to vary the strength of the effect. So here we're going to change the effect. Sometimes we're going to make it stronger than we observe. Sometimes we make it weaker than we observe, just by multiplying that coefficient by a number greater than or less than 1. And we can, again, do the same simulations. We can compare control, where we leave it exactly intact with this modified version, and we see what we get. And again, using the same kind of outcome, we get something that looks like this. So here's the observed case. And again, it's just like it did look before. And what do we see? We see that if we turn it off, we know if we go all the way to 0, this correlation goes up. And indeed, we can see that here as we would expect. Notice, though, it goes pretty quickly, actually. So we see that actually it does kind of matter. If you reduce by any substantial margin the observed level, you pretty quickly saturate. And at that point, it doesn't matter that much how much lower it gets. But what's really interesting is if you turn it up, what if we make turn taking an even stronger norm than it is? You really break the ICR correlation, and you break it really fast. So what this really says is that in these networks, or at least this particular network, the amount of turn taking, the turn taking reciprocity norm, is about as strong as it can be without it completely starting to break all the other sources of organization in the network. If it got much stronger than that, the conversations would become so sticky that people wouldn't be able to ever get rid of the baton, right? And so maybe that's a coincidence, but that could be an interesting insight. It's quite plausible that when organizations have to design things like SOP for using radio, they have to trade off between two things. I need to have enough turn taking so I'm sure that you heard what I said, and I heard what you said, you heard me saying what you said, right? But not so much of it that then you can't move on to the next thing. And so it's quite plausible that they've kind of socially tuned themselves around that key point. But at any rate, we can kind of see, again, these kinds of insights that are very hard to get otherwise, but with simulation, it's very straightforward. So this is an example where we can get something quite simple out of it. I think we're due to stop at this point, right? So given that, that we're now out of time, again, I want to, I've, as I promised you, given you a taste of what's in this. So again, I want to commend you to this document. All the other experiments we talked about, there are examples in here of how to do that with syntax you can run yourself, both somewhere in the WTC case, somewhere on the school network. You can find out what happens when you create an anarchy classroom and you take all the teachers out, what happens when you take a teacher out halfway through the class, what happens when you change how student gender is related to how they interact and so forth. These are just examples. There's an awful lot more, of course, that you can do with this kind of approach. But if I want to leave you with one message, it's the idea to not take your models for granted. You go to so much trouble, hours of computation to get one of these models. When you get the model, don't just say, well, I've looked at my p-values, I'm done here, I can go home. Use the model to get scientific insights, because every model embodies a theory. It embodies a theory about the world. The theory makes predictions. And we can use those predictions to get mechanistic insights and also to plan things like, how should I target people in a study? How, is my N big enough? All these kinds of questions we need to ask. And so having the ability to get these models, we can now use to probe the models to get all sorts of insights, and the toolkits are now there to do it. So hopefully you'll go out and then combine the great insights from the ancient days of agent-based modeling with the more recent insights from statistical network modeling to discover awesome new things, and then show how all of us old people were naive and should have done it right the first time. All right.
Questions before?
I hit everyone with a fire hose and no questions. Because I was so clear. Oh, we got a question here.
Can you do this kind of thing where we have multiple different types of actors? I know you did like a teacher student in one classroom, but can you do like multiple systems of contexts and how they all interact?
In principle, yes. I mean, you have to set the thing up, of course, and you have to estimate everything. But there's no reason in principle that you can't do that. And I mean, sometimes the engineering gets complicated, but you can also have there's a lot of very rich stuff you can do. So I give you an example. Some work that I've done with a guy named Sam Snow, who was a grad student at Yale and recently graduated. He's a zoologist, ornithologist specifically. He studies sage grouse. And he's the expert on this. I'm not a sage grouse expert, but he spent a lot of time in the field looking at sage grouse, and they fight with each other and they mate and they do all these things. So he wanted to understand what are the dynamics of sage grouse. They're called lekking species, so they have this big area called a lek where they go and the males will display and the females will choose them and the males fight each other. And so the question is what's going on in the setting. And it's a complex setting because it's nested. So you, for instance, have males that are fighting with each other. You have other males that are doing other things. You have females that are on the lek. And all of these things are going on at once. And so what we had to do was create a kind of, in a way, a multi-context sort of model where, for instance, when two males get in a struggle, they kind of become locked in that, and they can't do anything else because they are fixated on that fight. But meanwhile, other action is taking place that is not directly about what's going on over here. And so we have a whole sort of fighting subsection where once they get into a duel, they have these various things they do. And they have to do certain things to get out of the duel because the birds will lock each other into this and they can't escape. And that turns out to matter. It turns out at the end of the day, the biology that came out of it is that, maybe not surprising, although apparently surprising to some of the evolutionary biologists, fighting is not sexy to sage grouse. Shockingly enough, the females are not impressed at the males fighting with each other, which is what people had thought. They're not impressed at all. And fighting, in fact, is not so good for you because if you're fighting, you're not mating. So, in fact, some males really get screwed because they get into a cycle of violence where they start fights and then now other birds start fighting and they spend all their time fighting. And then meanwhile, the other birds are mating, while they're off doing that. So it raises the question, why do males fight at all? And sort of the answer is, well, if you can get in and get out and get away with it, you can deter the other males from later fighting you and interrupting you, and you may be able to chase off competitors in the lek. So if you can do a little fighting and be tough, and the big bird, that no one messes with, then you have an advantage. But if you miscalculate, you just become, enmeshed in an endless cycle of pain, and it doesn't help you at all. And so that was something that we learned by doing relational event models, on sage graphs. So there's just a lot of subtlety you can build in. Now that model required a lot of customization. It was not a trivial model to make. And Sam did all of that, so it's really, he's the guy who put this all together. But it's possible to do really beautifully rich treatments of very complex social systems with that.
Awesome, thank you.
You can find me later.
Really quickly, a little bit.